Hi friends, welcome to KnowHUB. So, here is the topic on which we are going to talk about. What is signal attenuation? Signal attenuation refers to the reduction in the strength of a signal as it travels through a medium. Inside a train, signal attenuation occurs due to the metal walls of the train which absorb and scatter the signal, making it weaker as it travels through the interior of the train. The signal is also affected by the train's speed and the distance from cellular towers, which can also affect the strength of the signal. Additionally, signal attenuation can also occur due to the presence of other electronic devices inside the train that can create electromagnetic interference. Also, if the train is passing through a tunnel or an area with poor network coverage, the signal strength can be further reduced. The amount of signal attenuation inside a train can vary depending on the type of train, the material of the walls and the distance from cellular towers. Generally speaking, the signal attenuation inside a train can be relatively high, making it difficult to maintain a stable mobile connection. What kind of wave is generated through mobile signal tower? Mobile signal towers, also known as cellular base stations or cell towers, transmit and receive radio frequency (RF) signals, which are a type of electromagnetic waves. These waves are generated by electronic devices called transmitters, which are located inside the mobile signal tower. The mobile signals are typically in the frequency range of 700 MHz to 2600 MHz, which are assigned to different types of mobile networks: 2G, 3G, 4G, 5G, and services. The radio frequency (RF) signals generated by mobile signal towers are typically in the form of sine waves. These sine waves are modulated with information, such as voice or data, before they are transmitted. The modulation process changes the amplitude, phase, or frequency of the sine wave to carry the information. For example, in a 2G network, the signal is modulated using a technique called frequency division multiplexing (FDM), where the signal is divided into different frequency bands and each band is assigned to a different user. In a 4G network, the signal is modulated using orthogonal frequency division multiplexing (OFDM), where the signal is divided into a large number of subcarriers, each modulated with a small amount of data. It's worth noting that the signal towers use many safety measures to avoid interference and to make sure the signal strength is within the safe limit for human exposure, as per the guidelines set by the regulatory agencies. Reason why inside train. The main reason for not getting a mobile signal inside a train is due to the train's metal body acting as a Faraday cage. A Faraday cage is a metal enclosure that blocks electric fields, effectively shielding the inside from any external electromagnetic signals. This means that the radio waves emitted by mobile phone towers are unable to penetrate the train's metal exterior, preventing mobile phones from connecting to a network. Additionally, tunnels and mountainous terrain can also cause signal loss while the train is passing through. How much does it affect? The amount of signal attenuation given by a train can vary depending on a number of factors, including the type of train, the material of the walls, and the distance from cellular towers. Generally speaking, the signal attenuation inside a train can be relatively high, making it difficult to maintain a stable mobile connection. The metal walls of the train can cause significant signal attenuation, with losses of up to 90 decibels or more. This means that a signal that is initially very strong outside the train will be almost completely blocked once it enters the train. Additionally, the train's speed and the distance from cellular towers can also affect the strength of the signal. The signal strength can decrease with increasing speed and distance, as the signal has to travel further and through more interference to reach the mobile device. It's worth noting that these values are approximate and can vary depending on the specifics of the train, the environment, and the cellular network. What is Faraday cage? A Faraday cage is a device that is designed to block the passage of electromagnetic fields. It is named after the British scientist Michael Faraday, who first discovered the phenomenon in 1836. A Faraday cage is typically made of a conductive material such as metal mesh, aluminum foil, or copper wire. It can be in the form of a room, a box, or other enclosures. The conductive material creates an electrostatic shield around the inside of the cage, which blocks the external electric fields from penetrating the inside. As a result, any electronic devices inside the Faraday cage are protected from electromagnetic interference. Faraday cages are used in a variety of applications, such as protecting electronic equipment from electrical storms, electromagnetic pulses (EMP), and radio frequency interference (RFI). They are also used in laboratories and research facilities to isolate sensitive electronic equipment from external electromagnetic fields. How skin depth is related to signal attenuation in train. Skin depth is a concept in physics that relates to the penetration of electromagnetic waves into a material. It is defined as the depth at which the amplitude of the electromagnetic wave is reduced to 1 about 37% of its initial value. The skin depth is inversely proportional to the square root of the frequency of the electromagnetic wave and the conductivity of the material. In the context of signal attenuation inside a train, skin depth plays a role in how deeply the electromagnetic waves of the mobile signal can penetrate the metal walls of the train. As the signal travels through the metal walls, it is absorbed and scattered, causing the signal strength to decrease. The skin depth of the signal is a measure of how deep into the metal walls the signal can penetrate before it is significantly attenuated. So, the thicker the walls, the higher the attenuation, and the smaller the skin depth, the higher the attenuation too. It's worth noting that in real-life scenario the walls of trains are made of different materials, and also the signal may be reflected, scattered and absorbed by other objects inside the train, making the signal attenuation even more complex.